everyone and welcome back to my channel. In today's video, we are going to cover something very interesting about the optimization side of things in C/C++. And this is more of a general topic or general discussion to have about computer science in general. And that is, what if we can turn a recursive function into the goto statements. The point of that is to reduce to eliminate the call overhead of the function, of the recursive function, which includes pushing onto the stack, popping onto the stack, but before that popping onto the stack and returning from where the function was called. So I picked a very simple function that I wanted to get turned into a goto sort of label, I would say. And just to showcase and demonstrate how difficult it is to convert a recursive function into a set of jumps. However, you of course get the benefit of great performance, and I've seen this in the C code base of Python, where somebody would have their own stack globally, something like this, and then they would wrap up their logic into a macro where they're doing the goto statements instead of writing a recursive function. But this really depends on many factors. What is my function doing? What is its logic? And what am I trying to accomplish? What is the actual performance trade-off I'm gonna get if I'm not using the recursive function? So in other words, is it worthwhile if you are using or calling your function in an expensive block of the code that performs millions upon millions of operations? It can be worthwhile. Or you just change your algorithm logic and there you go. And there is also something called tail recursion, which compiler detects if it sees primitive values as function parameters and arguments, so that it would be able to turn it into a loop, and this concept is called tail recursion. But that is not why we are here today. We're here today to turn a recursive function into a goto statement. So what happens when we call a function? We have a stack, and each function call has its stack frame. A stack frame consists of the function arguments, and what the function returns. The result of the function, the return value. So I commented out my return value here because I'm trying to write a void function, so I don't need a return value. It's just for simplicity I excluded this. And speaking of simplicity, I also made sure to use this, even though in C++ this will fill this buffer or array with blanks, and will call constructors of the call frame until we fill up the array. However, if you don't want to use that approach, you would just do something like this. And you should be good to go. But always make sure to have something like attribute always inline in that case if you're using something like this, so that there isn't too huge of an overhead in your code. I also make sure I do that. I do the same for the destructor because I don't really need it. It's all primitives. So to get back to the point, what does the call frame do? It's just pushed onto the stack to keep track of its calls. So that's why there's a term stack trace. So when we look at the function, we have to make sure, because even if you use goto statements here, you still need to recreate the call stack. Because when you call a function, at any point here, will you be able to access your argument of the current scope of the function. So if I call this function with 10, then I will, once I hit 10 here, it will return, get me here, and this is our base call. And at that point, we just keep returning, but until we get to that point, we execute the code. So we have to make sure, okay, how do I access my parameters? How do I access my arguments of a function? And that can be achieved if you recreate your own call stack, and that is done. So the reason I'm using split screen here is that I'm pointing out what is the translation of the call, of the recursive call. So this piece here would be the translation, or this piece here would be the translation of the if in the recursive call. Goto done would be the translation of return. And then we get to the call, where we call the recursive function inside, when we call a function inside of a function, right? And we have to make sure to push our current call frame onto the call stack, and then this would be our call. We go back over here, we check, do we return? We check with our base call, do we return or not? If not, we continue. And this job continues until this logic evaluates to true. So there is a lot to unpack here in terms of, okay, what if in my function I have something like this? And this is not going to work because it's a void function. But let's say I've returned something, and then I need to do another operation on here. Well, that is difficult to understand as we look at this, but the point is, what does the call function or call assembly instruction do once it's done with a function? It pops it and returns. So if we look at our implementation to the left, we'll see that here we get to pop our calls and return. So this would be the actual translation of it. And here you would execute your logic. Okay, I've gotten that return value of mine, and what do I do with it now? And here we go. That's how you would do it. But it wouldn't be n, it would be the return value of that call. But like I said, we excluded it for simplicity. But these are, if you're interested in this topic some more, I will make sure to create another video where we will actually be returning something. And then you will see how, how the complexity grows, and it's really sensitive. It's really like walking on eggs and whatnot. And I call that after code because I have a function call, I call it, I pop it, I return, and then I have the after code. Before code, I call just typical function body before I call my recursive function. So that would be the highest level translation of a recursive function into a Goto labels, where we can jump like directly. So here I'm doing a jump with a direct label. So my jump here is deterministic. Whereas if we had something like, I don't know, a computer Goto where I have a set of instructions or a set of labels. Now this is an indirect call. This is an indirect jump. So that is the difference between a direct jump and an indirect jump. So now let's get to benchmarking this. First, I'll benchmark it with no optimization flags, which would be O0. And we can see that the call performs so much worse than the Goto labels. So now if I optimize it via O1 optimization flags, we're still pretty much getting the same results, in that Goto labels being significantly faster than the function call. Alright, if I try to do this for O2 optimizations, that's not really going to work, because it will, once the compiler sees that my function doesn't do anything, it will just optimize it out. So you can sort of trick it by saying volatile number and then this, and you will trick it. Or will you? Not really. Because this function is quite simple, and I think the compiler just sees, okay, we're not doing anything with this. So anyway, that will be all for this video. If you're interested in more of translation from recursive functions into Goto labels, do let me know and I'll create another video. Okay, where we can cover a return value and not do a void function. Okay, thank you very much. I hope this was helpful, and I hope that you are gonna use something like this in your code base to hit that peak performance of your code and really do this kind of, shall we call it, micro optimization, but it's really at the grand scheme of things, it is a huge optimization, not just a micro one. But if you look at it at a low level, it is sort of under the microscope kind of thing. You really need to think about this stuff and think it through in order to make the significant performance improvement. Thank you for watching. Take care.